Okay, so just a few announcements here. Homework 7 will be submitted through Canvas. When I initially created the assignment, there was no online submission component, but now there is. I wasn't sure that we would be virtual today, so I just kind of put it up there as an ordinary homework assignment. But since it looks like we might be virtual for a couple of days, you'll have to scan your work as a PDF and submit online. Math seminar might be Wednesday. I will check with people and see if they're up for doing the seminar virtually, because it looks like campus may still be closed as of Wednesday. So I will have the details later this afternoon or tomorrow for you. Also, later in the week, I'm going to give you a list of what I'll consider essential definitions and theorems that will be fodder for upcoming quizzes. Okay, so just so we're all on the same page, quiz questions will come from this list of essential definitions and theorems. That list will grow as the semester progresses. Okay. So any questions? I think we got a few additional participants who joined us there.
I didn't get to make it to the office hours at 9. Is it okay if I wait to turn my homework in until I can make it to the office hours at like 2?
Yeah, that'll be fine.
Okay.
Okay, now let me see here. I believe the homework from 2-4 was questions 1, 2, 3, 4, and nope, sorry, that's 2-3. Looks like 2-4 was number 2, number 3, number 5, and number 8. I think, did I sneak number 8 in there on you on Friday?
Yep.
Okay. So talk to me about number 8. We're on page 61 here of the book. So we know that a series converges if and only if the sequence of partial sums converges. That's our definition. And it asks us to find an explicit formula for the sequence of partial sums. So who can help me out with that formula for 8a?
I got 1 minus 1 over 2k, or
All right.
2n, I guess.
Okay. That's a good start. So meaning this. Like that.
No, I have it written differently, but.
So what's different?
I have like 1 over 1 minus 1 over 2 to the k.
1 over 1. So 1 over 1
minus 1 over 2 to the k.
1 over 2 to the k. Possible. Let me see. I'm not sure. Okay. So the idea here is what kind of sequence or what kind of series am I dealing with? It has a special name. We know it from calculus.
Geometric.
Right, this is a geometric series. Okay. Now, if we have a finite geometric series, which is what the partial sums are, okay, the partial sums involve stopping at a fixed value. Okay, so let's call that big S. Okay, so we would have 1/2 plus 1/2 squared, 1/2 cubed. Keep on going till we get to 1/2 to the m. This is the key idea here. If I take this and multiply it by 1/2, well, what would happen to this? What would this turn into?
One over 2 squared.
Right, 1/2 squared, so it kind of shifts over this way. And this would turn into 1/2 cubed. Keep on going. There would be a term here that I haven't written. It would be 1/2 power m minus 1. That would turn into 1/2 to the m, and this would get bumped up. The power of 2 would be 1 higher. Okay. Now, this is something we actually talked about this in tech and programming. What do I do here? Why did I multiply this by 1/2? What's the next step going to look like?
You want things to cancel, so you
Right.
can like subtract them.
Right. We want stuff to cancel out because we want a closed expression. We don't want this open-ended thing with these dots. That's a problem when you're talking about a explicit formula. So what we do is we do a subtraction here. We take s minus 1/2 s. And when we do that, the middle terms all cancel. So we'd have 1/2 minus 1/2 power m plus 1. Now, how can I solve the left-hand side for s? What should I do?
I put 1/2 s equals.
Okay, good. So that's where you ended up getting that, right? So if you have 1/2 s, go ahead, yeah.
I think I did some algebra wrong on that one.
I think it might actually work out because if you multiply everything by 2, there you get your 1 minus 1/2 to the m. So that looks like it works there. It's not the way I was expecting this to go. I was thinking something a little different, but that's okay. Because I was thinking about the formula that I know for the finite sum of a geometric series, which is like 1 minus r to the m plus 1 over 1 minus r. But I think that all works out in this. Okay, so that will work. So for this geometric series, we can get an explicit formula for the partial sums. And once you have this, what do you think it converges to?
1.
Right, it should converge to 1 as m goes to infinity, because this fraction gets smaller and smaller and smaller, the larger the exponent is. So that's what we would expect there. So the geometric series is one of the only series where we can actually find the sum that it converges to. All right, so the tests that we know from calculus 2, like the p-test and things like that, they tell us whether or not a series converges, but they don't tell us what the series converges to most of the time. But for geometric series, we do have a formula. And these other two series are what are called telescoping series. So what do you think that means, telescoping series? Okay.
The next,
oh, go ahead.
like the next term helps cancel the term before it.
Yeah, basically the kind of terms in the middle end up canceling each other out, and it's kind of the name comes from not like a big telescope that you have on like a mountaintop observatory, but one of those little spyglass telescopes that you see in pirate movies, right? And when they're done using the telescope, they just kind of collapse it into itself and just have that little cylinder rather than the elongated version. That's what they mean when they say telescoping. It's maybe collapsing is a better word. And the idea, for example, on part C is using a property of logarithms, the way logarithms treat division. So each term here can be written as a difference, log of the top minus log of the bottom. And the idea being that the bottom term, or the bottom part of the expression here in one term, is equal to the top of the next term. So those two middle terms would cancel each other out. Okay, so these two guys are telescoping series. All right, so that's the idea with those. So I'd like to move on to the next section here, which is section 2.5. And it's about something called the Bolzano-Weierstrass Theorem. Okay. There are a couple of names you have to know how to pronounce to have cred as a math student. This is one of them. How do we pronounce this one again?
Euler.
Right, that's Euler. Okay, and here's another one of those names. It's of course quite tricky if you haven't seen it before. Some people might pronounce this like a W, and they might say Weierstrass or something like that. But it's a German name. The W is actually pronounced like a V. So Weierstrass. Okay, Weierstrass. He was a mathematician in the 19th century. That's the 1800s, and that was a time when calculus was being put on a much more mathematically rigorous footing than it was in the time of Newton and even Euler. Okay, so Weierstrass is kind of responsible for our modern notion of what we would call analysis. Okay, so the key ideas. For this section. Okay, this will be something that goes on our list of essential definitions. Definition of a subsequence. And you should be able to give me a sequence and be able to produce examples of subsequences of that sequence. And of course, we need to work on understanding the Bolzano-Weierstrass theorem. Okay, now on that list of essential theorems for quizzes, the simpler ones I might very well ask you to prove on a quiz. Like that idea we had on the last quiz, where we had two convergent sequences, and the theorem was about the new sequence that we form by taking the sum of the terms converges to the sum of the limits. I'd consider that a fairly simple theorem to prove and would be completely comfortable asking you to prove theorems like that on a quiz. This one I might ask you to state. Okay, it's a little more involved, the proof, but I might ask you to state something like this on a quiz. Okay. So let's talk about subsequences. Okay, let me consider this sequence right here. Okay, so -1 to the n over n. Is this a monotone sequence?
No.
No, not monotone. It's switching sign every time, right? So the first term is -1. The second term is +1/2. So that you're going up there, and then -1/3 back down, +1/4 back up. So it's oscillating. All right, so the monotone convergence theorem does not apply to something like this. The sequence does converge. We could prove it directly from the definition, but the monotone convergence theorem would not apply here. Okay, so let me look at some terms here. Okay, so we'd have -1, 1/2, -1/3, 1/4, -1/5, 1/6, -1/7. That we'd keep on going like that forever. Okay, so these are the values of the sequence. Okay, I want you to tell me if the thing I write down is a subsequence or not. Now, I know I haven't given you the definition of a subsequence yet. Okay, but the purpose of this little experiment is to help us understand why the definition of a subsequence looks the way it does. So just based on what you would think a subsequence is, so make a reasonable guess as to what subsequence would mean, and tell me if you think what I write down is a subsequence. How about I do this? What do you think?
Yeah.
Yeah, I would guess so. We're kind of just taking the first, the third, the fifth, the seventh. Basically, we're just taking the odd numbered terms, the terms with odd indices. Okay, so we would say yes to this. We would expect yes. How about this one? A little tricky. What do we think about this?
I think, yeah.
Certainly there's, it seems reasonable that it might be a subsequence. What's weird about this one, though? It has some things in common with this one, in that in the first one I gave you, I selected only half of the terms, basically, right? Even though you'll allow me to abuse notation that way. Of course, we've still got infinitely many terms, right? But I'm still taking every other one. But there is a little bit of a difference here. I'm just taking the even indices as opposed to the odds. But if the odds make a subsequence, so should the evens. But there is also a little bit of a difference.
They're out of order.
Right, they're out of order, right? In the sequence, 1/2 came before 1/4. And 1/8 would be over here after 1/6. So I've shuffled the order of the terms. And that actually disqualifies this as a subsequence. Okay, so for a subsequence, we're going to need basically two criteria. Number one is every term in our subsequence should be a term in the original sequence. You can't just throw in new stuff, and that's what we would expect. The second thing is the terms in the subsequence have to appear in their original order. You can't shuffle them like we did with this second example. Okay, so if you look with me on page 62, let me see if I can get this in here. Okay, definition 251. So AN is our sequence. And notice what they've got here. N1, N2, N3, N4, N5 is an increasing sequence of natural numbers. Then this is called a subsequence. Okay, so K sub N indicates the subsequence. All right. So this is what they've got down here. Notice the order of the terms in the subsequence is the same as in the original sequence, and repetitions are not allowed. That's something we didn't actually check in our example. Okay. So on page 62, you've got your definition. So maybe star that, mark it down, write it out. That's a definition I might ask you to reproduce on a quiz. And as I mentioned, I'll give you a list of definitions I think are important and will be eligible if for a pool of quiz questions. Okay. So notice some things we've got here, right? The first sequence that we're dealing with is like this. N sub k is equal to 2k minus 1 for k in the natural numbers. In other words, right, we're taking 1, 3, 5, 7, etc. And our subsequence looks like A1, A3, A5, dot, dot, dot. Okay, and the reason that this one ended up getting messed up is because here we've got A4, A2, A8. Oh, please don't run out. I just started. A6, dot, 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 right? So the subscripts here aren't forming that increasing sequence, right? 4 is greater than 2 here. My subscripts are supposed to be in increasing order. Okay, so that was the difference there. So I'll just make a little note in our notebook. So definition 251 needs to be committed to memory. Okay, so the Bolzano-Weierstrass theorem. Basically ties together two ideas from the last section and the one that we just got introduced to here, the idea of a subsequence. The Bolzano-Weierstrass theorem says that every bounded sequence has a convergent subsequence. Okay, and just a quick note here. There may be many convergent subsequences. Okay, so the Bolzano-Weierstrass theorem is a theorem about existence and not necessarily uniqueness. All right, now this is related to a theorem that we've already talked about. Okay, so give me a theorem that we've already talked about that this is kind of like, somewhat similar to. What does it make you think of?
MCT.
Okay, right, the monotone convergence theorem. Now, what does that say again? Remind me of that.
If a sequence is increasing or decreasing
Okay.
and is bounded, then it converges.
Okay, right. So if a sequence is bounded and it is monotone, in other words, if it's an increasing sequence, what's the fancy name that we say for increasing, where we kind of hedge our bets a little bit there?
Non-decreasing.
Right, non-decreasing. So if a sequence is non-decreasing or non-increasing and bounded, then it converges. Okay, so the Bolzano-Weierstrass theorem has bounded in there again. So in a way, the collection of sequences to which this theorem applies is a little bit bigger than the collection to which the monotone convergence theorem applies. Right? The monotone convergence theorem applies to sequences that are monotone and bounded. The Bolzano-Weierstrass theorem, which I'll just abbreviate BWT, applies to bounded sequences, not necessarily monotone. Let's look at a quick example here. Ooh, ha ha ha. Yeah, okay. Let's do that challenge. Okay, so I'm going to give you a sequence that is bounded but not monotone. This one does not converge. But the conclusion of the Bolzano-Weierstrass theorem says that this has convergent subsequences. There exists a convergent subsequence. Okay, and of course, we know what the terms look like, so help me out here. You guys take the first two.
One's going to be like all ones, and the other's going to be all negative ones.
Okay, right. So we can get two right away. That was why I kind of paused and I said, oh, should I make it just two? But there are ways to produce other convergent subsequences as well. Okay, so one convergent subsequence would be this one right here, -1, comma, -1, comma, -1, comma, dot, dot, dot. Okay. And then this subsequence, well, how are we choosing the subscripts, the n sub k's? Well, it looks like we're pulling the odds, right? Because when n is odd, this gives us a -1, okay? So here, the subsequence that we're looking at is A1, A3, A5, dot, 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 like that, okay? And one thing to note here, we've kind of used this maybe without really proving it as a theorem. If you have a sequence that is constant, then that sequence converges. Okay, you can very easily prove it from the definition. Because given any epsilon greater than 0, the difference between the terms and your target is 0. So that's going to be less than any epsilon, no matter which index you're choosing in the sequence. Okay, but that might be something I put on the first test. Okay, be able to prove that if a sequence is constant, then that sequence converges. Okay, so this is our convergent subsequence. It converges to -1. Another convergent subsequence was this one right here, 1, 1, 1, 1, dot, dot, dot. Okay, how are we getting the n sub k's here? What's the formula for n sub k?
$2K.
Right, 2k. You're picking the evens. In other words, you're looking at A2, A4, A6, dot, dot, dot. That's your subsequence, and this converges to 1. Okay, now this is sort of to emphasize that your subsequences don't need to be, you know, things like this, just the evens, just the odds. You're allowed to mix them up a little bit. You can't go too crazy and put things out of order. But I might choose n sub k to be this. Two k minus 1 if k is less than 100, and 2k if k is greater than or equal to 100. Okay, so that's how I'm choosing my indices. Okay, so tell me what this sequence looks like. What do the terms look like? What's happening to them?
You'll have a whole bunch of negative ones until you get to the 100th term, and then you'll have a whole bunch of positive ones.
Right. So what does the sequence converge to? So we have 100 negative ones in a row. And then, or actually, I guess 99 negative ones in a row. And then after that, we have ones. So what does the sequence converge to? It does converge, by the way.
To 1?
Yeah, it converges to 1, okay? So that's another thing to, oops, I turned my video off entirely. I wanted to switch. That's another thing to keep in mind. It's something we hadn't really talked about, and it might be beneficial to just make it explicit. When we're talking about a sequence converging, what matters is what happens in the tail of the sequence, what happens at the end. The beginning does not affect it. You could have if your sequence converges, you could take the first 10,000 terms and change the first 10,000 terms. As long as you don't mess with the stuff after that, your sequence still converges. You could change the first 1 million terms. As long as you don't change the tail, the sequence still converges. Okay? So it's the stuff that happens at the end that determines convergence, not the stuff that happens at the beginning. Okay. So the Bolzano-Weierstrass theorem guarantees the existence of a convergent subsequence in that case because our sequence is bounded. As we saw, we got at least 3 of them there. We could create many more if we wanted to. We just kind of mess with this a little bit. You want to create a total, not totally different, but different one, just add a 0 to this. That's a different subsequence that also converges to 1. Okay. So here's the idea of the Bolzano-Weierstrass theorem. We're going to make use of something called the nested interval property. Okay, this is something that we discussed in chapter 1. Okay, could you remind me what this is? The nested interval property. It's a consequence of the completeness axiom. Okay, now remember, mathematicians are not creative with names, and that's good. Okay, so the nested interval property applies to intervals. Okay, we know what those look like. They're segments on the real number line, right? What does it mean for them to be nested?
They're contained by the one for it.
Right. Each one is contained in the previous one. Okay, so if we do a quick review here. So I1, I for interval, right, contains I2. Okay, so in other words, I2 is a smaller interval than I1, and it's contained inside it. I3, ... If that is a sequence of closed nested intervals, then this is true. Oops. Okay. So what is this saying right here? What's the punchline? Then I've got this thing. Tell me what it's saying in math and what's it saying in plain English.
The intersection of all of them is not empty.
Okay, right. So we take the intersection of all the intervals and we have to get something that's non-empty. Another way to say that, there exists X in R such that X belongs to this intersection. And there may be many such X. Okay? So the proof of the Bolzano-Weierstrass theorem is going to use this nested interval property. So some more ideas for this proof. The start of our theorem is we have to be given a bounded sequence A sub n. Okay, so A sub n is a bounded sequence by hypothesis. Thus, there exists capital M. Okay, so we're using our definition of a bounded sequence. So there exists capital M so that absolute value A sub n is less than capital M. Okay, and let me make it less than or equal to. So there exists a positive real number M such that A sub n is less than or equal to capital N for all natural numbers n. Okay, so this means that negative M is less than or equal to A sub n is less than or equal to M for all natural numbers n. All right, and that's coming directly from this. Okay, but don't be shy about doing a minor restatement of something. sometimes that minor restatement can get you started on the right path here, okay? So what we have here is the interval negative m to m contains infinitely, actually it contains all a sub n, which is infinitely many, of course. Okay. So here's what we're going to do. We're going to take this interval and we're going to cut it in half. Okay, so we'll have two intervals. Okay, so we take this interval, we cut it in half. At least one of these has to have infinitely many of the ANs. And the reasoning is, well, if this statement were false, then this only has finitely many and this only has finitely many. But we know that if I take both of them together, I have all the ANs, which is infinitely many. Okay, so this statement can't be false, so it's got to be true. All right, so we choose I1. Choose I1 to be that interval. Okay, one of these has to contain infinitely many a sub n's. If you have two of them, then you just get to pick. All right. Now the strategy is keep cutting that interval in half. Okay, keep cutting that interval in half, and through that process, form a sequence of nested intervals. Okay, so let's say we start with the positive half. Let's say 0 to m had infinitely many. All right, cut that in half. Now you've got two intervals. The first interval is length m, then you got two intervals length m over 2. One of those has to have infinitely many a sub n's. Pick that one. Okay, cut that one in half. Now you got two intervals length m over 4. One of those has to have infinitely many a sub n's. Pick that one. That's your I3. And then you keep on going, getting a sequence of nested intervals. You have to have a non-empty intersection. And because we've been getting intervals that are length m over 2 power k at each stage, you're eventually going to run out of room and you'll have to have exactly one thing in there. Okay. So I want you to read through the proof of the Bolzano-Weierstrass theorem on page 64. Ooh, messed up because it's reflected. Okay, messed up the lighting there. Read through on page 64. And I want you to get started with problems 1 and 2 on page 65. Okay, there's a bunch of parts to those. Okay, so try to get started on those as soon as you can. Okay, I do have office hours this afternoon, and I sent out a Zoom link for those. Okay, any other last minute things?
Yeah, I got a question.
Yeah.
Will we be able to correct the quiz that we did last time we were in class?
Yeah, I will figure out a way to get those to you.
Okay.
Since there's only a handful of you, I might just scan them and send them out to you.
That works. Appreciate it.
Okay. All right.
Thank you.
Oh, thank you. I'm going to end the meeting and head to my next class.